Hi, my name is Lauren Cruz, and I'm an environmental health specialist with the Hawaii Department of Health. Thank you for joining us today for the last of our four-part webinar series on groundwater basics. So today we'll be focusing mostly on contaminant plumes and groundwater cleanup options. And this webinar will consist of a 20-minute presentation followed by a question and answer session. So if you have any questions on the material that's being presented, please type them up in the Q&A section at the top of the screen, and we will try and do our best to get to as many questions as we can. In addition, at the end of this webinar, there will be a survey posted in there and we would greatly appreciate if you take just a couple minutes and complete it for us. Today, I'm joined by John Jacob, Wayla Lee, Bob Whittier, and Dan Bernal. So Dan, why don't you get us started for today?
Thank you, Lauren. Let me go ahead and share my screen. Okay, well, welcome to webinar number 4, the last of our 4-part series on groundwater. And this webinar is going to discuss contaminant plumes and aquifer cleanup. And so let's first review what we discussed in webinar 3, some of the mechanisms that affect the fate and transport of contaminants in the groundwater. And so we talked about, for example, if we have a spill and the contaminants migrate downward through cracks and crevices and reach the water table, and if the groundwater is flowing to the right, then in the early time after a spill, contaminants will migrate down through these preferential pathways of connected, fractures and permeable zones. And over time, the groundwater will carry the contaminants. And as the groundwater carries these contaminants, the contaminants will follow again these higher permeability zones. And after a longer period of time, these contaminants can migrate, different distances away from the source area. And so this mechanism by which the contaminants are carried by the moving groundwater, we call that advection. As part of that, we have different speeds and velocities that the groundwater moves, and that causes some dispersion of the contaminants to form the plume, and we call that hydrodynamic dispersion too. Another important mechanism for contaminant fate and transport is absorption. And here, as the groundwater carries these contaminants, sometimes they will stick to the volcanic rock and also organic carbon, and we call that process adsorption. And over time, though, as groundwater continues to move and the chemistry changes, these chemicals can unstick too, and we call that desorption. Now, another important mechanism that we talked about is the idea of diffusion. And if we think of a cup of water and a dye in it, then these dye molecules will essentially start spreading out because the molecules are actually jiggling at the microscopic scale because of the temperature. And because of that, the contaminants will then, and dye will spread out and eventually be relatively evenly distributed in the water. And so we call this diffusion, the process by which chemicals can spread from higher concentration to lower concentrations. And another mechanism that we talked about in groundwater is biodegradation. And here, these naturally occurring microbes in the groundwater, in the aquifer, can actually degrade and break down the chemicals. They like to eat them, some do, and some like to breathe them, and will transform these chemicals into less harmful chemicals. Now, in this talk, we're going to focus more on remediation. And as part of that, we need to understand better some of these mechanisms that can make remediation take a longer period of time to clean up the groundwater. For example, that process of desorption, when the groundwater can be cleaned up, let's say by pumping the water out and it gets cleaner, then this desorption will add more of the contaminants back into the groundwater. And so that process can slow down the cleanup time. Another important mechanism is the idea of back diffusion. And so as these plumes migrate out, they also will diffuse, they'll spread out into the more massive zones of the volcanic rocks, for example, in Hawaii. And so that mass gets trapped in the denser zones. And as we clean up the permeable zones, that mass can back diffuse into the permeable zones. And so again, this back diffusion mechanism can also slow down the cleanup time frame. So let's now look at how we collect the data for groundwater quality. And so to do that, one standard way to assess the groundwater quality is to use groundwater monitoring wells. And so we have to drill holes into the ground. And on the left, we can see a rig that's typically done to drill these holes into the ground. And also then we have to build and install a monitoring well. And so these monitoring wells, when they're completed, will look like this. And once these monitoring wells are installed, there's going to be a number of them depending on the size of the plume. We'll then sample those wells to try and map out the distribution of where the plumes are in the subsurface from groundwater impacts. So as part of this process, when we have these monitoring wells, we want to assess the groundwater quality, then we'll have people in the field go out and collect groundwater samples. And so here's a picture of that process on the left. Those are monitoring wells. And what's really done is that we'll first measure different indicator parameters to make sure we're getting a representative groundwater sample. So we'll measure the pH, the conductivity, and the temperature. And once those are stabilized, then we'll go ahead and collect the sample and package it, and then send it to a laboratory for analysis. And so there's, because we're looking for potentially different types of contaminants that include metals and also volatile organic chemicals and semi-volatile chemicals. These different chemicals will require different laboratory techniques by the chemists in the lab to measure the concentrations in these samples. Now, once we get that groundwater chemistry back from the labs, then we will then try to construct a map of the three-dimensional extent of these contaminant plumes. And so as part of that, though, we have to have a good monitoring network to make sure we understand where the groundwater plumes are, where the high concentrations are and low, and to monitor over time, especially if we're going to use some remediation to clean it up. And so typically what will be done is, some borings may be drilled to figure out where the spill occurred. Monitoring wells are typically a few wells may be installed near the source area where the highest concentrations are. We'll typically have a background well too to look at the background groundwater quality. And also we like plumes to be on the edges of where the impacted groundwater plume is. And we also will put some wells, since the groundwater flow is this direction and the plume is moving this way, we'll put in wells along the center of the plume. And in particular, we like to have a sentinel well and also compliance well to protect any down gradient receptors, such as water supply wells or even surface water. And so once we get that chemistry data, then we'll construct these maps where we equal concentration levels to determine how the plume is distributed. And this is a very symmetric plume. In Hawaii, the geology is very complex. And so these plumes can be very irregular too. So once over time, as we're monitoring the groundwater quality at each of these different monitoring wells, especially if we're doing remediation, then we want to look at the trends of the concentrations over time, because the goal is to make sure that the groundwater reaches their cleanup standards. Okay, and so here's a couple examples of concentration versus time maps. And so there's many samples have been collected over, it could be decades or even longer. And so there's different trends that can occur in each monitoring well. For example, this well on the left has a lot more variability. It looks like it has a decreasing trend. It hasn't reached the cleanup standard, but there's a lot more variability in this well. Whereas this well has a clear decreasing trend, and there's less variability. And each well is going to have its own particular signature depending on where the well is the complex geology. Now, once the plumes have been delineated and we understand where they're at, then there's going to be a complex decision-making process for how to address the impacted groundwater. And so as part of that process, we certainly have to have detailed sampling plans to collect the data. We have to then manage the data and organize it in databases. We may construct maps of the data, like we showed those plume maps, or possibly 3D visualization. We may perform groundwater modeling to try and design the remedy in terms of recovery wells and where to put them. And also, risk assessments are performed to make decisions as to what type of remedy should be selected for that particular site. Now, let's move on and discuss now how groundwater is remediated when impacts are detected and risk assessments indicate that remediation should be performed. And so we can categorize remediation in two categories in general. We can have in situ remediation, and that's where the groundwater is treated in place. We can also have ex situ remediation, and that's where the groundwater might be pumped out and then treated, and it might be re-injected, or it might be discharged. And so we'll look more carefully in the next several slides at these different types. We'll look at, for example, something called soil vapor extraction, chemical oxidation, permeable reactive barriers, and the bioremediation that occurs as part of the in situ treatments. And then for the ex situ, we'll look at pump and treat, where we pump the water out. We'll look at how we can use multi-phase extraction and some of the other technologies for treatment. Let's first look at vapor extraction. It's sometimes called SVE. And so this is usually used to treat contaminants that are trapped above the water table in the unsaturated zone. And so this colored area here is impacted soil. And so what soil vapor extraction does is it pulls the air out of the subsurface using a vacuum pump. And so as it pulls the air out, these chemicals, and this is typically for chemicals that vaporize and are volatile, like benzene, okay, and trichloroethene. And so as we pump the vapors out, then these the air that's pumped out. And over time, this can be effective in treating the unsaturated zone and the impacted soil. Some of the disadvantages, though, are that if you have highly heterogeneous zones with permeable and impermeable zones, then sometimes you'll need a larger number of these extraction wells, and sometimes the air, when it's pumped out, will short circuit, and so we may not be able to get the vapors and contaminants out of all these zones. It can be trapped sometimes in the lower permeability zones, and so we have to keep that in mind too. Another remedy that's done is called air sparging, and this is done for below the water table, and it's typically done in conjunction with that soil vapor extraction that we just talked about. And so what air sparging does is we inject air into the subsurface, and when the air is injected below the water table, then it's going to make bubbles, and these bubbles will then cause the contaminants, and typically this is going to be, again, usually to treat the volatile chemicals that vaporize, like benzene and TCE. And so as these bubbles are pushed into the aquifer, they will then cause the vapors from the groundwater to move with them, and then they can then be essentially pumped out by above the water table as these vapors move up and extracted by soil vapor extraction. In addition, by introducing the air into the groundwater, that causes it to have more oxygen down there, and that oxygen can help enhance remediation by activating the bioremediation and helping microorganisms to help treat the groundwater and clean it up even faster too. Another technology is in situ chemical oxidation, and this technology is effective for a wide variety of chemicals. That's one advantage that it has, and so what is done in in situ chemical oxidation, sometimes called ISCO, is we have these reagents or things that light the chemicals and break them down into harmless chemicals, and so these reagents are injected below the water table into the zone where the impacted groundwater is, and it could be even DNAPL, dense non-equal phase zones too, of separate phase. And so as the reagent is then injected in there, it reacts with these chemicals and breaks them down into less harmful chemicals. And so this treatment can be used in at many sites. There are some limitations. It's hard sometimes to deliver these reagents right to the zones where we would like, especially if there's low permeability zones. It takes a long time sometimes for chemicals to get into the low permeability zones, and it's going to take a long time to get them out, and it may not be easy to access when we inject these chemicals. So that's one limitation. Another in situ remedy are these permeable reactive barriers, PRB. And so these are typically used when the groundwater, when the water table is shallow, because what we have to do is we have to dig a trench and then put in these barriers. And these barriers are reactive materials. And so as the groundwater migrates through the barriers and it carries the contaminants through the barriers, these reactive materials on the barriers will treat the groundwater so that the groundwater coming out is cleaner. And these technologies are effective. Sometimes they can be used, with bioremediation, where you can add also some nutrients to enhance the bioactivity to further remediate the groundwater. And again, the one limitation is, though, that we can't go too deep with this technology. It gets too expensive and not practical. Okay, and so now we'll move to the ex situ treatments, where we take the groundwater out by pumping, for example, and treat it. And so we call that pump and treat. And so, for example, if we have some zone of contaminant plume, and let's suppose the groundwater is going this way, then typically, we'll want to put these recovery wells where the highest concentrations are, and maybe also near the edge of the plume. And what we'll do is we'll pump the groundwater out, and when you pump the groundwater out, it lowers the water table and it creates a capture zone. And so contaminants within the capture zone cannot migrate out, and eventually they're going to migrate. As we pump, they'll slowly migrate to recovery wells and be taken out, and then they'll be treated. Okay, and so groundwater modeling is typically used to try and design the configuration of these recovery wells so we can have hydraulic capture and to assure that of the impact. Another is multi-phase extraction. And so here, for example, we have an LNAP. Yes?
Oh, we missed the last part of, you cut out for the last part of the previous slides. I didn't know if you wanted to finish and go back over that again. Sorry.
Oh, sure. Yeah. Okay. Let's go back to the previous slide. And so I was talking about pump and treat. And so again, these recovery wells will pump the impacted groundwater out, and then it'll be treated. And as part of that, we want to, make sure these wells are placed in a location where we're getting good mass removal so we can reduce the concentrations more rapidly. And groundwater modeling can be performed to design where to put these recovery wells so we have a capture zone so the impacted groundwater cannot get out too. And so that's the technology where we extract the water and then treat it. And so for multi-phase extraction, the idea here is that we may have, for example, LNAPL, maybe some diesel fuel or gasoline migrated and is floating on the water table. And so we have a layer of hydrocarbon there. And so multi-phase extraction can be used to deal with the fact that, some of these contaminants will volatile saturated zone, for example, above the hydrocarbon, and some will dissolve into the groundwater and form a plume. And so this multi-phase extraction technology is designed to take air out and clean the air, also to pump the LNAPL out, the actual pure phase materials, and treat it, and also pump the groundwater out. And so it can deal with each of those three phases. And so that's multi-phase extraction. Now, another remedy that can be used, and typically it's done as these other technologies tend to be, reaching a point of diminishing returns, then many sites will then transition to monitored natural attenuation. And so monitored natural attenuation is the process by which natural mechanisms of the subsurface can, for example, lead to biodegradation of the plumes, and also the microbes can naturally, eat and also breathe these chemicals, and there's also volatilization, and so over time the natural attenuation can also, reduce the concentrations over time, and so, for example, with natural attenuation, we'll still need a good monitoring network. If the groundwater is going here, we want to make sure that we have the plumes, many wells to examine concentrations throughout the plume and make sure we have decreasing trends so that this remedy is effective. So one question that's commonly asked is, why does groundwater cleanup take a long time? And so there's many factors, and one is that, it takes a long time for these contaminant plumes to form and grow and diffuse into the volcanic rock, for example, and it's going to take a long time for it to diffuse out and be cleaned, and many of these contaminants like to stick to the sediments, and so if we're trying to pump the water out, then the ones that are stuck to the sediments, as I mentioned before, that desorption is going to slow down the cleanup process. And many contaminants also, do degrade slowly. And so that's going to mean it's going to take a longer period of time for these contaminants cleanup standards. And some contaminants can have very low cleanup standards. And so that means it's going to take longer for them to reach the levels where their cleanup has occurred. Now also, and this is a very important factor, especially in Hawaii and at many sites, is that the geology, if the geology is very complex, then that can affect how fast we can clean it up. And if you recall, for example, the volcanic, layers form from different lava flows over time. And this picture we looked at before, this is a cliff. And so we had these higher permeability zones, and then we also had the more massive zones. And so as contaminants, if we're, for example, put down deeper, these layers also occur like this. And so typically we're going to pump the groundwater from the more permeable zones where we can get water out. And these permeable zones, this water in these permeable zones can be cleaned up. However, that back diffusion mechanism I mentioned, where contaminants diffused into the more massive zones, well, as we clean up this zone, then these contaminants are going to back diffuse back into the clean zones, and that means we're going to pump potentially for a longer period of time to get the groundwater cleaned up. Okay, and so and there's also, as we'll talk about in the next slide, there's some limitations also in the remediation technologies, and so that's what causes these cleanup times to be very long and can be decades to centuries for some sites. So let's look more carefully at some of the reasons why, we have limitations in our remediation technologies. Well, again, if chemicals have very low cleanup standards, like 1,4-dioxane, for example, or TCE, then it's going to take, it can be difficult to treat these chemicals with those low cleanup standards. In addition, as I mentioned, these chemicals can be stuck to the volcanic rocks and organic carbon, and desorb into the main permeable zones. And so accessing these chemicals that are in the low permeability zones turns out to be very difficult. As I mentioned, if we're doing, for example, chemical oxidation, it's hard to deliver those reactants to where the chemicals are, especially if they're in low permeability zones. And as I mentioned, back diffusion is another problem that can lead to taking longer periods of time. We may clean up the groundwater, but then contaminants can back diffuse into the groundwater and cause us to have a longer period of time to sites that cause contamination, had been operating for a long period of time with leaks to the subsurface. They can build large plumes that could be over a mile long, and the bigger the plume, the more difficult it is to remediate the entire zone of the plume. So again, it can take periods of time, depending on the types of chemicals that we have, the size of the plume, and the complexity of the geology. And so also just the process of performing remediation, is very complex. We can have, some sites, especially industrial sites, can have a wide variety of different chemicals. We can have metals, inorganic compounds. And so if there's a large suite of different chemicals, then that might require, more than one remediation technique, because as we mentioned, soil vapor extraction and air sparging can only deal with the volatile chemicals. And so we might need multiple technologies in order to clean up these plumes. And some sites are rather remote, and so it might be difficult to get equipment to those sites. And these cleanups can take decades. And so over that period of time, as we monitor the cleanup, there might be different remedial measures that may have to be designed and performed as part of the cleanup process. And so as part of the remedy operation, we have to make sure and perform monitoring to assess how fast the cleanup is occurring and whether we're going to reach cleanup goals. And so we call this long-term monitoring, or LTM. And this monitoring, is performed in the wells that we in our monitoring network to evaluate, how the cleanup is occurring in different parts of the plume. And so, for example, the goal is to eventually, get the contaminants concentration levels below the cleanup goal. But even then, subsequent monitoring will be performed to make sure that they don't, there's no back diffusion and they don't go back above the standards. And so there'll be a period of a year or more of monitoring to make sure that the standards remain, the concentrations remain, below the cleanup goals here. And so lastly, in short, please remember that the groundwater is safe. The water is treated before it's sent to any homes. And also, there's, essentially federal, state, county, and local agencies that are all working together to protect our groundwater resources. And so, for example, the Department of Health has different agencies that look at, the monitoring data that's collected for impacted groundwater. And also there's assessments for corrective actions if necessary to protect our groundwater resources. In addition, there's water plans that are performed in terms of water quality plans to protect the groundwater. There's water resource protection plans. There's agricultural plans. All this is part of making sure that we protect this important groundwater resource. Remember, 85% of the groundwater is used for drinking water. And so we want to make sure that this resource is sustainable into the future. Thank you for your time, and we really appreciate you attending our webinars, and hope you have a great day.
Thanks, Dan. Why don't we go to some questions? The first one we have is for Bob Whittier from the Safe Drinking Water Branch. Hey, Bob, where are the labs that the samples are collected and sent to located?
Okay, we do have a limited amount of analytical labs here on Oahu, but most of our work gets sent to the mainland. Popular, or a very large laboratory is Eurofins, and they have multiple locations, a lot of them on the West Coast. And that is one reason why we have the longer turnaround times on the results, is we have to collect a sample, pack it, and ship it to the lab, and then they, in the mainland, and then they have to do the analysis and get back to us. But the most of the work is done for our work on the West Coast. Thank you.
Hey, Bob, so an add-on to that is, how long does it take to get the test results typically?
Well, typical turnaround time is 2 weeks, but you can request a quicker turnaround time to get it in less than a week at a higher cost, of course.
Thanks, Bob. The next question, I'm going to take it's so other than soil vapor extraction, are we employing any other methods of groundwater remediation? Why or why not? So I am aware of that we have used air sparging and ground soil vapor extraction as a combination together at one site. There's also been sites where there's been ISCO used, so the in situ chemical oxidation. In the state, I believe we don't think we've used any of the like the Dan, what were those barriers?
The permeable reactive barriers.
Yeah, we may have used it once. May have seen it used once in the state, but I'm not really sure on that one. But I think the bulk of them actually have been used at various sites over time in the state of Hawaii. So, okay, and then the next question, Bob, is for you, Bob Whittier from the Safe Drinking Water Branch. Bob, how long does it take contamination to spread across an entire island?
Well, first off, it won't spread across an entire island because groundwater is going to flow from areas of higher groundwater elevation to lower. So basically, Mauka to Mackay. Also, there are geologic barriers that can prevent lateral groundwater movement, such as deep valleys and the highly weathered rock beneath them, or our volcanic dikes that come up and separate, for instance, the windward side of Oahu from central Oahu. So basically, groundwater is going to flow downhill. We may encounter some barriers along the coast, such as caprock, that will cause it to flow somewhat laterally, but it still has to find those lower elevation exit points. So we won't get contamination across an entire island. It is basically constrained by the geology and the physics of groundwater movement. Thank you.
Thanks, Bob. The next question is for Dan. Sorry, Dan. Hold on, let me find this. Oh, there we go. Okay. So how is it typical to use a combination of remedial technologies to clean up a site?
Yes, I think it is. Certainly when we do air sparging, we want to do the soil vapor extraction with it. But at some sites, we may, use chemical oxidation to try and treat the very high concentration zones, and then follow it up with, essentially recovery well pumping, pump and treat, where we then pump the residual levels out to try and, clean it up quicker. So yes, we can combine several remedies, and some of these will transition into monitored natural attenuation over time too.
Okay, thanks, Dan. Well, we're a little over noon, and so if we were unable to answer your question or you think you have more questions once you've reviewed this, please feel free to send us an email at curtis.pruder@dohawaii.gov. In addition, if you don't mind taking a couple minutes to complete a short survey, that would be great. It's the link to it's located in the Q&A at the end. Thanks everyone for joining us. Appreciate it. Have a nice day.